Now let's implement the erase function. We continue to use the same data. So T1 is defined and then those data are inserted. So here let's call erase function and then provide a data. Then from this T1 tree, a node which holds data 5 should be completely removed from the binary search tree structure. That's what we expect. So let's implement such a function. Public interface void erase. The data, integer data is specified. And then private recursive implementation. So after erasing a node from the tree, the root may be updated. So return type is a node pointer erase function based on given tree. The data will be removed. So let's implement those functions. So in public interface void BST erase integer data, then we may want to assert that the root pointer is not null, so tree should have some data, it should not be empty. Then root p may be updated after erasing from current tree root p and this data. So here private recursive implementation is it may return a new updated root erase. Then it takes a node which is root of the node. So on this tree, let's delete, erase this data. So we are going to design this function recursively. And step 1, solve for trivial size. If root is a null, empty, then just return null or r, the same value. That's a trivial case. If not, if the data to be erased is smaller than the data at the root of the node, then that data should be removed from the left subtree. So recall the recursive function design procedures. Step 1, solve for trivial size. So we have done this one. Step 2, assume any smaller size solution is available. So here in this specific case, smaller size means we know how to erase from left subtree, because left subtree is smaller size. Also, we know how to erase from right subtree, because right subtree is smaller. So assumption means that we can erase data from left subtree or right subtree. On step 3, using those assumptions, step 2, and solve for current size, the assumption at step 2, and then any known facts is there. So here, so we are utilizing those assumptions. So let's maybe continue to write the program. So if the data to be removed is smaller than the data at the root, then the data should be removed from the left subtree. So we call erase from left subtree and then erase this data, and this may update the root of left subtree. It's there. So else if data to be erased is greater than the data at the root, then similarly the right subtree may be updated after erasing the data from right subtree. There. Then else part is a complex part here. So in else part is then we come to this case if data to be removed is in the current root node. So let's have some picture to illustrate this part. So we have some tree like this, and so on. So if the data to be erased is compared with the root and the smaller, then we go left subtree. Otherwise, we go right subtree. So we go either left subtree or right subtree. And eventually, we will find data at the current subtree root. So you may keep going down, and then at this moment, we have some tree there, but here now we find that this node has a data to be removed. Then it may have some subtree of its left or right subtree and so on. So that is at else case. In else case, we could consider three cases. Here, three cases means as follows. So let me draw a picture for that. So we come down and then come down and then we find the node. This is to be erased. That it may have both left and right subtrees. So we are going to erase this node. It may have both left and right subtrees. The case number one. Case number two is that it may have only one subtree. So left subtree only, or it may have a right subtree only. Case number three, the node to be erased has no subtrees at all. It is a leaf at the end of the one. So we need to consider those three cases. So let's consider first case. In the first case, we are going to erase this node. We are going to erase the node. Removing the data means after removing the data, we need to free this node, which was dynamically created by the insert operation. So if we remove this node, then we do not keep the binary search tree property. If the node is gone, so if this node is gone, then we have one edge and another edge, another edge. So we cannot simply put those edges together. Then this kind of a connection is not allowed in binary search tree. Binary search tree, if you remember, it should have only two edges from a node, but edges are connected without any node. That is a violation of a binary search tree property. So we should do some other ways. So to implement case number one, we have two choices, two algorithms. That is, the first one is from the binary search tree property, we know that all the data in left subtree is smaller than the one at the root. So if I have a data here as n, then all the data in left subtree is smaller. So instead of physically removing this node, just keep this structure, but what we do is find the largest value from left subtree. Largest value will be keep going right. The rightmost one will be largest value. If we pick up largest value from left subtree, we could simply copy the data here, largest value here. Instead of physically removing this node, just find the largest data from left subtree and then simply copy the data, and then when you remove physically, instead of removing this node, just remove this node physically. Then we keep the structure and we keep the binary search tree property. Another way, very similar idea, is that instead of doing so, just find the smallest value from right subtree. Smallest one from left subtree, and then that would be on the very leftmost edge corner. You will find the smallest value. So copy the smallest value up to the node that was identified to be erased. So just copy the smallest value from right subtree, then erase or physically deallocate this node, the smallest value node, from a right subtree. Then we keep the binary search tree property. So in our implementation, we will choose this second option. So find the smallest value from right subtree and put that data on here, the node to be removed. Then instead of physically removing this node, just removing the node which had the smallest value. So let's try to write code for that. So in else case, is that the node should be removed. The node has the data, so it should be physically removed. So case number one, as we find here in this picture, from the rightmost node, then find the smallest value and the copy and do so. So here, let's identify case number one. Case number one is if the node has data and the left is not null, and then the node right subtree is not null, then this is a case number one on this picture. Then what you do is find, so this is both left and the right subtree exist. That's the case. So find the smallest value from right subtree. So min data is we have defined the find min function for this one. So find the min function, as you call that, that one will return the smallest value from right subtree. So we say from right subtree find the smallest value, and that is here we return, we get that. Then we copy the min data on the current node. The current node is R. On current node, we just copy the smallest value from the right subtree. Then we erase the node which had the smallest value from right subtree. So we are going to erase from right subtree the smallest data as we found earlier, and then this may update the right subtree root value of that. So since the right subtree is again smaller size, we can just utilize assumption. Any smaller size solution is available. So this part is case number one where both left and right subtree exist. Then else case of this one is case number two here, the node to be removed, erased, has either left or right subtree only, or no subtree at all. It seems we have two different cases actually, but this is only one case, so we can just put them together. But here, in this case, 2 and 3 case, what we need to do is here the situation is that the node to be erased has only one of the two subtrees. So here's a subtree left or subtree right. So what you need to do is set the bypass link. So from here, just the bypass or go bypass this one. So this operation is identical to pop of a stack or pop of a queue operation. So just set the bypass link, save the address of this node, set up the bypass link, and then free the memory. Same thing. So let's write code for that in else case. So here else case is only one subtree exists. So what you do is bypass that R is going to be R right or R left. So R is a pointer to the node. So R right or R left, depending on which is not null. So see that if R left is not null, then left subtree exists. Then R is updated by R left. Question mark. Otherwise, R right will be updated. So this question mark column ternary operation takes care of that. So see, at this moment, only one subtree exists. So if left subtree is not null, then we do R equal R left. So set up the bypass link. So if this is not true, left subtree is null, then we assume that it's a right subtree. So right subtree, we set up the bypass link. Of course, if we set up the bypass link, the address of the node to be removed is gone. So we save it in discard the temporary variable. R is saved. Then we free the memory after set up the bypass link. So when all of those things are done, we should return the updated R. So R may be updated here or there and so on. So we need to return the updated root for that. So here, this one is taking care of only one subtree exists. However, this logic also covers or no subtree. That is, when you set up the bypass link down here, so we assumed that there is a root of a left subtree or root of the right subtree. If there is no subtree at all, then this root will be null. So we just set this one null, or if this is null, we just set this null. So this equation statement covers that if there is no subtree, since both left and right are null, we simply assign null into there. So it's taking care of the third case as well from this picture. So the erase function is implemented. Now let's test that for. So let's first do compile. If any error occurs, so there's no error, then we can test how this works. So in main function, we are going to erase data 5. Then we should be able to see the structure of the tree after deleting 5. So earlier we have defined traverse breadth function there. So using that, let's see how this function works. So compile the program, and as we run it, then this is the result after deleting 5. And then let's double check whether this description is correct or not. So we are testing with the data we have used so far. So the picture is 10, 5, 15, and then 4, 12, 7, 20, 6, 14, and 13. So at this moment, if we erase 5, so this is gone. The algorithm, since a node with a 5 has both left and right subtree, what you do is from right subtree, we find the smallest value out of that. That is 6. So 6 is copied into this node, and then we physically remove node 6, setting this one null. That's the algorithm says. So if we do this way, the structure of the tree is that 10 has 6 and 15, 6 and 15, that's correct. 6 has 4 and 7, 6 has 4 and 7, and the 15 has 12 and 20, and the 4 has a null null, 7 has a null null, 12 has a null and null and 14, and 20 is null null, 14 is a 13 and the null, and the 13 is null null. So this description, traverse breadth, correctly describes the binary search tree after erasing data 5.